Hello there, Mr. Sutton here, bringing you the IM3 Honors 4-2 Part 2 homework solutions on max and min. On this one, the number of minutes it takes S students to complete a puzzle is given by this T function. So this is kind of interesting because T is the output, time is the output, and the input is the number of students. We want to know how many students should work on our puzzle and how long it'll take them to complete it. So presumably, how many should work on the puzzle together. We're trying to minimize the amount of time it's going to take the students to complete the puzzle. So in order to find the minimum value here, since this is a quadratic, it's a parabola if you graph it out, we just need to find the vertex, and the input value for the vertex is going to be the number of students that should work on the puzzle. The output value of the vertex will tell us how long it'll actually take them to complete it. The good news is this formula is already in vertex form of a parabola. So it's just going to be, my vertex is just going to be positive 4 because of this s minus 4 in here, comma positive 20 because of this positive 20 over here. So 4, that represents the number of students who should work on our puzzle. So the s value of our vertex is 4 students. And 20 represents how long it will take them. That's the t value of the vertex, is 20 minutes. So those are the values we need for this one. For this problem, we have a rectangular pen made with 100 meters of fencing on 3 sides. The 4th side is going to be a stone wall, so we only have 3 sides that we have to worry about. We want the greatest possible area of this enclosure and the dimensions that give that area. So let's start with a picture. Here's our rectangular pen. Here's the stone wall, and we also need to come up with something to represent the different sides here. So since these left and right sides are going to be the same length, and I need to make something an unknown because I don't know going into this problem how much fencing I have on each particular side, I'm going to say the left and the right side, I'm going to make those X's. And then for this last side here, that's going to be whatever's left over when I take away X from the total fencing that I had to start with. Since they gave me 100 meters of fencing in the beginning, I lose 2X from that for this 3rd side. So I can write 100 minus 2X. And now I need a formula to kind of tie it all together. Ultimately, I want to maximize the area. So let me write an area formula. In general, area for a rectangle is base times height, or length times width. In this case, my length I can represent as 100 minus 2x, and the width I can represent as x. And it doesn't matter if I do that backwards either, just as long as you have one of each. So we have 100 minus 2x times an x giving us the area. This is now the algebraic formula that we want to maximize. Now this is a parabola when we graph it out. It's in intercept form. So probably the fastest way to find the max is just to see what zeroes out each of these factors. So for this first factor, 100 minus 2x, if I plug in 50 for x, that would zero out this first factor. And then 0 would zero out this x factor here. So we have 50 and 0. Those are my zeros. And I know that the greatest possible value of this function is going to happen at the vertex, which is halfway between the zeros. So if I average these together, that'll give me the x value at which I can find my greatest area. So 50 plus 0 over 2, just averaging those. And this is also going to be the value of x here, the width. So that's going to give me 25. That'll be 25 meters. And now to figure out the length, I can plug that into this 100 minus 2x expression. So that's 100 minus 50, which gives me 50 for the meters on that. So I have basically 25 times 50. Now to find the maximum area, you could just do 25 times 50, or you could plug x back into this original expression here. I think it's less work if you just do 20 times 50 though. And let's figure out what that is on the calculator. So plugging that in real quick into the calculator, 50 times 25 gives me 1,250, and that's going to be in square meters because that was area. On this one, the artist, Vinnie Van Gogh, produces P paintings per year 2 years after his girlfriend breaks up with him, according to this function right here, this P function. we want to know when Vinny is most productive and how many paintings he produces that year. So we're basically trying to maximize a quadratic function. Now we know the maximum value of a quadratic like this is going to happen at the vertex. And as luck would have it, they've actually given us this function in vertex form. We can pick the vertex right out of here the way this is written. So let's write out the vertex first. And this is going to be t values and p values instead of x and y values. So the t value of my vertex is going to be whatever I'm subtracting from t inside this squared parentheses. So that's going to be 12. And the p value, the output value, the y value of my vertex, is whatever's being added outside the squared parentheses. So that's this 36 right here. So that's our vertex. So then the year during which Vinny is most productive is just the input value of this vertex, which is 12 years. And the number of paintings he produces that year is the output value of the vertex, the y value. So that's this 36 right here, and that's going to be in units of paintings. For this one, suppose 85 meters of fencing is available to enclose a rectangular garden, one side of which is against a house. We want the dimensions of the garden that gives us the maximum area, and the area. All right, well, let's draw a picture. Here's a rectangle, and here's the house that counts as one of the sides of the garden. So just setting up some variables to represent the lengths, the dimensions of this garden. These two sides on the side left and right are both the same, so we'll call both of those x. And if those are both x, then there's 85 minus 2x of fencing left over for this third side. If you've used up 2x here, then subtracting that from 85 gives you this other side. So we've done this so that we can express all the dimensions in terms of a single variable. That's going to allow us to write a formula now. The formula for the area of a rectangle in general is length times width. In particular, using our variables here, the length we can call 85 minus 2x, and the width we'll call x. So now I need to figure out the vertex of this quadratic function in order to get the maximum value. Vertex for something in intercept form like this is just going to happen at the average of the two zeros. So let's find the zeros of this function. For this first one, 85, let's see here, if you subtract that and divide by negative 2, that's going to be 42.5 for that zero. And then zeroing out this other x here, that's just going to be 0. So the width is also going to happen to be the x value of the vertex, which is going to be 42.5 plus 0 all over 2. And let's just use the calculator to start helping us here because we're going to need it eventually anyway. So 42.5 divided by 2, that gives us 21.25. So that's in meters, and that's going to be the width of our garden. To find the length of the garden, we do 85 minus 2 times what we just found there. Basically 85 minus this 42.5, which is another 42.5 meters. So those are our dimensions. For the area, we can just do length times width. We have a length of 42.5 times a width of 21.25, and for that I will use the calculator. So plugging that in the calculator, we end up with 903.125, and that's going to be in square meters. That is our maximum area for this garden. On this one, we have a population of seagulls after X years growing. According to this Y function here, we want to know in how many years the population reaches its minimum and how many seagulls that's going to be. Okay. So we're trying to find the lowest point on a parabola, basically, which is going to happen at the vertex. So let's first find the vertex, and then we'll figure out which value represents the number of years and which value represents the number of seagulls. The good news is that they gave us this in vertex form. So we just need to figure out the vertex by picking out some numbers from the way this is written. So the x value of the vertex is going to be whatever I'm subtracting from x inside this squared parentheses. So that's a vertex value of 8 for x. And then the y value of the vertex is just whatever I'm adding outside the squared parentheses. So that's this 46. So this means that the seagull population reaches its minimum at 8 years, because that's the input value in this function. That's the x value. And then the number of seagulls at that time is the y value of the vertex, so 46 seagulls. For this problem, I'm trying to find the maximum rectangular area enclosed by 600 meters of fencing. So let me start by drawing a rectangle. And I need to figure out some variables or some ways of expressing these different sides. Let me start by making this side x. Got to start somewhere, right? Well, if this side is x, that means this other side, which is the same length, is also x. And what about these other two sides? Because if I'm talking about area, at some point I'm going to have to do length times width, so I need a way of expressing these other sides as well. So I've used up 2x worth of fencing, 2x meters of fencing, however much that is. I had 600 meters to start with initially. So that means there is 600 minus 2x meters of fencing left over for both of these other two sides combined. Individually, then, they each have half of that much. So 600 minus 2x divided by 2 is going to be 300 minus 1x. So I've got 300 minus 1x for this side and 300 minus 1x for this other side. Again, because combined they have to add up to 600 minus 2x. All right, so my area formula I'm trying to maximize, that's going to be length times width. My length in this case I can call 300 minus x, and my width is just going to be this x variable here. Since this is intercept form of a parabola, I know since it's a parabola in general, the maximum value happens at the vertex, and since it's intercept form in particular, I can find the vertex by just finding these zeros and averaging them together. So the zeros of this function, we're going to have 300 for that first parentheses, and this x here gives us a 0 of, well, 0. So I'm going to average these together. That's going to give me the x value of the vertex for this parabola. And it's also going to give me actually the width, because that is what x is that width there. So I'm going to say the width and x, both are the same thing. And specifically, it's going to be 300 plus 0 over 2. Again, we're averaging those zeros together to get that vertex value. So that's 150 if I divide 300 by 2. So 150 meters in this case. Now I have to go back and let me find the length, because I'm going to need that to use this area formula if I don't want to just plug stuff in for x. So my length is going to be 300 minus 150, which is also going to be 150 meters. So basically the best way to do this is to make a square out of the fencing. That's the most efficient shape here. So to find the actual area, I need to multiply my length and width together. So I have a length of 150 times a width of 150. And we could do this on the calculator. You might know that 15 squared is going to be, normally it would be 225, but we've got 2 zeros to go along there as well. So it's going to be 22,500 square meters.